Hi everyone, Dr. Mandis here, coming at you to talk just a little bit more about gas laws and our series of gas laws, problems, theory, whatever. In this particular video, I want to talk about basically density and partial pressures. We have a lot of different gas laws. Density is probably the one that, I don't know, the math is one of the easier maths. It's not as easy as Dalton's law, but the density kind of gets people caught up. So I really want to talk about how density relates to molar mass. Dalton's law problems are things that once you see them, you go, oh yeah, that makes sense. Okay, for the most part, people just make sense. So out of our list of problems that you see there, we're going to focus on Dalton's law and density. And first up, I'd like to talk about density. Okay, and for density, basically, we need to just chit chat about what it is. Density is a ratio of mass to volume. Okay, and that's all it ever is. But in gases, although mass doesn't change, mass is pretty much a constant, you know what I'm saying? The mass of a sample. But the volume, when you get to gases, the volume's going to really change based upon temperature and pressure. I mean, everything expands and contracts based on temperature, but gases to an extreme. Okay, and because it relates, volume can relate to temperature, pressure, number of moles, all that sort of jazz, we have special things for gases. Okay, so let's look at that. Not that I babbled long enough, but density is m over v, and the ideal gas law is PV equals nRT. Well, what I want to do is I want to rearrange this equation for volume, and then I can sub it in for volume over here and do a little bit of math solving for density. Alrighty? And in that case, you get this groovy little m over n ratio, not m and n, but m over n. And basically, that's mass per mole, and that is molar mass. So now we have a pretty powerful thing. Now we have molar mass tucked in there. Alrighty. So P RT times M is density. Later on, you're going to also see that as another way. Potentially, you could say, hey, molar mass is moving RT and P over there, dirty, DRT over P. And so some teachers you might have seen this from your teacher, molar mass equals dirty P. They probably wrote a better M than I did. And it's just a nice way that you can remember it as dirty P. Although I think this is more useful because 3 times out of 5 you're solving for density, not molar mass. All right, but we'll do both in this video. Okay, what you should realize is, hey, density and molar mass are going to be related because if you have a bunch of gases, like in the room you're in, you have a bunch of different gases. They're all at a total pressure and temperature that's kind of at the same. Their pressures is temperatures. So the density of those gases is really going to relate to the molar mass. But anyway, let's do an example problem. Consider you got two gases. A is 10 grams per mole. B is 30 grams per mole, and both are at the same temperature and pressure. So which has the greater density? Well, you should be thinking, hey, let me write the equation. Always write general equations. It's a good habit to be in. So if I have that, I don't have temperature and pressure, but I know their molar masses. And I'm not asked for the specific densities. I'm just asked which is greater. You can measure two people and say, you can look at two people, I should say, and say, hey, who's taller? You don't have to measure their heights. You just put them side by side. You can tell who's taller. Well, here we have them side by side. Okay, 10 grams versus per mole versus 30 grams per mole. Well, 30 grams per mole is going to be more dense. Okay, so you don't need to know, again, don't need to know the values of P and T. Don't get caught up with that. All right. Sometimes if they're asked for the specific density, you actually want to calculate the density, then you're going to know the values. But for the most part, you don't have to. Okay. Here's an example where you have the values. You can say, hey, density of carbon dioxide gas at that pressure and temperature. Well, again, make your list of your unknown, which is something I totally encourage you to do. You see that, hey, you got density, molar mass, pressure, and temperature. What equation do you have that has all that in it? Solve it up for density because that's what we're solving for. All right, here's that different way of writing the equation. Molar mass equals dirty P. If you did that, you got some algebra to do. If you start with what I said, hey, it's easier to just do PM over RT. That's density. The reason we're not writing, M, and I'm not writing M, but I'm writing M is cursive M is molar mass. That could be molarity. Okay, this is mass, molality. I mean, it could be a bunch of things. So that's why we do the curly QM for molar mass, if you were wondering. But anyway, we can solve it up for density by just plugging in and going. How do you know which R value to use? It's the same gig as we did with the ideal gas law. The pressure is in kPa. So if we don't want to convert pressure, find an R value that's kPa, that's 8.314 kPa. Okay, so kPa is going to cancel kPa. If you look at your units, mole is canceling mole. Kelvin is canceling that little Kelvin down there. And if you look at what's left, you got grams per liter. I'm pointing at this one right there and that liter way down there. And so density is in grams per liter. But I learned in like ninth grade, density was grams per milliliter. It's mass per volume. In this case, our unit of mass is grams and our unit of volume is liters so that it can cancel. Hint, hint, hint. If you're in a lab dealing with the density of gases or something like that, you're probably going to measure your volume in milliliters. You really want to convert that to liters so that things cancel out of the ideal gas law. Another example for density, something that I like to bring up with students is, hey, why does a balloon float or sink to the ground? Okay. You should realize, hey, less dense things float, more dense sink. As far as balloons go, things in water, well, let's compare it to water. Well, your balloons are in air. So compare it to air. Well, air is mostly nitrogen and oxygen. So, hey, it's about 30-ish grams per mole. Nitrogen's 28, oxygen's 32, 30-ish, okay? So what you really want to do is say, hey, are you more dense, a greater molar mass than 30, or less dense, a lower molar mass than 30? So here I got my groovy little green marshy guy and my blue little Smurfy dude, and they have their balloons. Why are some floating and some sinking? Well, look at the molar masses, okay? Helium is 4, hydrogen is 2, okay? Xenon is a wickedly high, 131, and krypton's 85. Those are a lot more than air. Helium and hydrogen a lot less than air. So yeah, 2 balloons will float and 2 will sink like a rock, okay? So you can compare to air if you want to know just about a balloon, or in that case like a Zeppelin or a dirigible. Why do they float? They're not lighter than air. They're less than as far as density goes. Okay, but anyway, you got Dalton's law of partial pressures. I like to just bring up quickly. Okay, Dalton's law basically, remember, pressures are collisions. So with the walls of the container, so the total amount of collisions is going to be a sum of, well, the collisions. Okay, how many gases do you have colliding with a container, or a percentage? One gas collided 80% of the total. Well, it's 80% of the total. Chi, the mole fraction, is the percent of the decimal. Once you know these equations, they're not so bad to work with. So two quickie problems here. A flask has a mixture of nitrogen and oxygen gases. If you know one partial pressure, what's the other one? We're at STP, and I did this on purpose. That's code for total pressure. If it's at that total atmospheric pressure, that would be your total pressure. So if you're in lab, again, collecting gases or something like that, your atmospheric pressure is usually the total, and then you have their 2 gases that you collected or something like that. In this case, P total is just the sum of everybody. Well, how many gases do we got? We got 2 gases. I used 1 and 2 because I was lazy and I just copied it over. You could write PN2, PO2 if you wanted to. Okay, but anyway, P total minus P1 is P2. Plug them in and go, and you got 60 kPa. You have to know that your STP is 101.3 kPa. Why did I use kilopascals for my standard pressure? I thought it was 1 atmosphere. Same thing. They're the same thing. But my pressures were given in kPa, so I just used standard pressure in kPa so I could subtract more easily over here. If your teacher's a tool and they want to mess with you, they'll give you pressures that are different units, and you're going to have to convert them so you can do the subtraction. All right. Lastly, let's do a percentage gig without really be given the percentage. Okay. In this case, I got a flask, 3 moles of neon, 2 moles of argon. Total pressure is 10 atmospheres, partial pressure of argon. Don't wig out about it. Okay. Think, hey, I got a bunch of pressures and I need to know partial pressure. I could be using the one where I add them up, but I'm probably going to use that one with the chi because I don't have a bunch of partial pressures. Pi equals chi times P total. Chi is the percentage of the decimal. It's the fraction. Okay? Well, you know the fraction of argon. You really do. It's 2 moles out of the total. Total of 5. I read 2 moles plus 3 moles so you could see where 5 moles was coming from. 2 out of 5 is a percentage as a decimal. So we just do the math, and hopefully I did the math right, and you get 10. I mean, you get 4 out of 10. Anyway, this is Dr. Mandis. Have a lovely day. I'll talk to you later.